So statistically, online classes for 100 level across campus have a 3% lower pass rate. Online OChem statistically has a 50% worse pass rate online.
50% worse pass rate?
50% worse.
Whoa.
As in, like, 65 to 70% of the class doesn't pass online OChem. It's yeah. It's. I
knew it would be bad.
We have a student. He's actually one of our PLAs, who I'm not gonna say which one, but he took OChem 2 online 7 years after taking OChem 1, and he got a B. And that's like the most high-fiveable B ever, because anyone who can get into OChem 2 after almost a decade off and do it online is committed. Yeah, should be committed. Okay, so we're going to go into reactions of alkenes. We're going to start with the mechanisms that are very familiar because we've been using it as our core example for electrophilic addition, and then we're going to start modifying it and adding layers to more types of alkene reactions as we get into it here. So what we've done so far, let's see if this works, is we have an alkene which has these extra electrons in the pi bonds, and we've got, we'll say, hydrobromic acid. So we can have a nucleophilic attack where, because of the dipole here, we are rare in electrons on the hydrogen, rich in electrons on the bromine. In addition to that, the bromine is a nice electrophile, so it can hold an extra pair of electrons and be pretty happy doing so. So we can take these electrons in the double bond, attack the proton. When we do this, as we start to form this bond, we're exceeding the duet on the hydrogen. This causes this bond to break, pushing the electrons to the bromine. Notice every time I do this, I'm pushing with a double-sided arrow because a pair of electrons are moving. And this gives us this intermediate with bromine as a bromide. Now, at some point, people have probably wondered, so where does the charge go and where does the proton go? That's probably occurred to a couple of you at this point. And we're going to delve into that a little bit more today because sometimes it can go either spot, sometimes it'll bias one direction, and sometimes it'll go exclusively a particular direction. So we'll start to address that in a second. But once we have our high energy intermediate, we have a second nucleophilic attack where these extra electrons can move to satisfy the positive charge on the carbocation and attach the bromine. So this is the overall flow or rationale for what we've been working with. And we can apply this to all kinds of compounds, anything with a double bond. So if we have a cyclohexene and not only does it apply to all kinds of compounds with double bonds, this applies to all kinds of hydrogen halides. So we've got hydrofluoric acid, hydrobromic acid, hydrochloric acid, hydroiodic acid. All of these are going to add in the same way, where we can have an alkene attack the proton, break the bond, push the extra electrons to the halogen. The halogen then does a subsequent attack on the carbocation. So any of these can come in here and participate in the reaction. So if this is hydroiodic acid, we can get the same type of reaction, which will give us carbocation. In this case, the charge could be on either location, and then the iodide can come in and do another attack on the carbocation. And we've substituted this iodine using the electrons from the double bond. Now, here we go. Let's look at a scenario where we don't have symmetry in the compound. Try a different color. So when we do this, how much detail do we want to do? We'll do a lot of detail. What's the first step?
Double bond. Hypothesis.
Where's the positive charge go?
Tertiary carbon.
This one?
Yeah.
All right, some people have been reading ahead. We'll make that a 3 since we already decided. So in this particular case, the carbocation could theoretically go to either side of the double bond. However, not all carbocations have the same stability. So what turns out is that a carbocation which is attached to 3, we'll just not even say methyls, we'll just say 3 R groups. And an R group is any carbon chain. So it could be a methyl, could be an ethyl, could be a propyl, could be a butyl, doesn't matter. R is just a good placeholder for it. This is a tertiary carbocation because the carbocation is attached to a carbon which has 3 different R groups attached to it. This is going to be significantly more stable than a secondary carbocation, which has 2 R groups attached to the carbocation. It has just a proton here, which we can't, we'll talk about why protons are not as stabilizing in a second. Then we've got primaries. Oh, gotta get the charge on there, or it's not a carbocation. So if it only has 1 R group attached, it's primary. And if, worst case scenario, it has no R groups, this is a methyl cation. So this is the order of stability, with tertiary carbocations being by far the most stable, secondary being moderately stable, primary not being stable, methyl being even more not stable. Oh, last class, I made a note that I totally ignored on this. There was a question about temperature doesn't drive equilibrium. And I looked into it a little bit more, and it turns out that temperature actually does change equilibrium, but just not in the way that you think it does. Because heat production can be considered a product. So if you change the temperature of the reaction, it can drive it based on Le Chatelier's principle with heat being a product. However, if you heat a reaction in a heat-producing reaction, that's like adding product to the product side, which actually pushes equilibrium the opposite direction. So you can influence the equilibrium constant through the addition and subtraction of heat, just not in the way that you probably were intuitively asking the question, based on competing rates. But I had to now I have to say I was wrong. Scientists hate being wrong. But we're wrong all the time, so we have to get used to it eventually. So in this case, we have a tertiary carbocation because this is a T-butyl carbocation, and here we have a primary carbocation because we have 1 carbon attached to it. So this, in this particular case, this will nearly be 100% formed because tertiary is so spectacularly preferred over primary. If this were secondary, there'd be a mixture of products with this one being preferred. But when you compare tertiary to primary, it's nearly 100% preferred to be tertiary. So once we've identified that this is our preferred carbocation, it makes predicting the product pretty easy because we've got our iodide, which can do our second attack, and this is our product, instead of having the iodine hanging off of this carbon over here on the side. So the question can become, why are all of these methyls stabilizing? And this is a really nice explanation. And we actually have the tool in our toolbox to explain it, because we used it to discuss the more stable conformers of ethane. What's the term? Somebody was reading the book clearly. Hyperconjugation, right? So hyperconjugation, in the case of ethane, we have freedom of rotation here, but not all conformers are of equal energy levels. And we found that the methyls being 180 degrees away from each other in the staggered position was the most stable, even though we didn't have significant spatial interactions between protons and methyls that were steric in nature. So, and remember, we have this sp3 with antibonding orbital, and we've got this sp3 with antibonding orbital, and then we were bonding that to our, well, these are sp3 to sp3 actually, because these are methyl. And we can get from, when these are aligned perfectly, we get some through space sharing of the electrical density in our bonding orbitals with our antibonding orbitals, like a very, very, very weak version of a pi bond. And this is a stabilizing factor which explains why this is more stable. Well, in this case, we get to pretty much the same thing, where if we're just evaluating the carbocation, what we're going to have here is a vacant p orbital. Where we have a positive charge, because it was a p orbital, because we had to have a p orbital available, in non-hybridized p orbital available to do the pi bond. And then over here, after we've bound the first proton in that first nucleophilic attack, here, we have our sp3 hybridized to s sigma bond. And we can get that same kind of sharing which helps pull some of that charge. And this makes sense because we have electrons here, we have positive charge here, and we can help satisfy the positive charge a little bit by balancing it with some of that hyperconjugation. So the more carbons we have with hydrogens around this carbocation, in this case we just have, this is primary. If we had 2 carbons we would be able to share it 2 different ways. If we had 3 carbons, we'd be able to share 3 different ways. Now, this isn't all the time. Remember, these have freedom of rotation here also. However, in the same way that an ethane conformer is going to exist more often in its more stable form than its eclipsed variations. These also will exist as conformers in these kind of supported hyperconjugated variations as well. Any questions so far?
What is this called?
Hyperconjugation. This effect of getting a little electrical density traveling from the bond to the aligned antibonding orbital. Yes.
So I have a question about, I understand how the carbon to hydrogen sigma bond orbitals can overlap.
Mm-hmm.
Can you draw how the sigma bond of the carbon-carbon bond would do the same thing?
Sigma bond and the carbon-carbon bond. You mean like here?
Yeah.
So it's about alignment of orbitals. So orbitals are just places that electrons can exist around a nucleus. And we have different orbital solutions for different numbers of electrons. So when we start to form bonds, what would be our best solutions for where we can put electrons in atomic situations is going to change into these hybridized scenarios. So in this case, this is going to be sp2 because we have 3 bonds that are planar. So we've hybridized 3 of our bonds, and we have a vacant p orbital here, which is housing the positive charge. So it's just a vacant orbital that doesn't have any electrons in it yet, which is why we have the positive charge there. And then over here, once we have any of these 3 bonds aligned so that they are lined up like this with that vacant orbital, because like this it can't hyperconjugate, like this it can't hyperconjugate, but once we get to here, we can hyperconjugate a little bit, and this electrical density in this bond can be supported by this vacant p orbital with a positive charge in the same way that this one can be supported by this antibonding orbital. And this one can be supported by this antibonding orbital.
Right, but in the second example of carbon, that can happen with the carbon-carbon bond as well as
the carbon-carbon bond itself is just a standard sigma bond.
That can overlap.
Oh, sorry. This bond here is a sigma bond with 2 electrons that are stably shared between it. The electrons being shared here, it's not a new bond. It's just a little bit of through space sharing from a more stable bond to a vacant higher energy location that is not currently occupied by electrons. Yeah. I'm not sure, maybe okay. Sometimes people have, students are better at interpreting what a question is. I know, I think I'm just not answering the question.
So in the book it said both carbon, hydrogen, carbon, and sigma bond.
Oh, so if this was a methyl.
Yeah.
Oh. So then we would just be, instead of a carbon to hydrogen, which would be sp3 to s bond, it would be sp3 to sp3 sigma bond, but the bond can still share electrons in exactly the same fashion. Okay. Whew. No, that's good. That was a good question. It took me a second to figure it out. Any other questions on this? Yes.
I was just confused on your drawing.
That's fair.
On the end of the red C.
The red C. Okay.
Is that the bottom of the H? What was that thing you just erased?
It wasn't another vacant orbital. It was.
Okay, it had an H on it.
Yeah.
Okay. And just that H is bonding to those other guys.
Currently, this is the only one that's in plane with these because
Okay.
this one's sticking out of plane away and this one's out of plane towards. However, if we rotate it at 120 degrees, this one could be up here and this one could do the exact same thing.
And it's rotating.
Yeah, it has ability to freely rotate. Just like conformers of ethane when we were doing that Newman projection. Same thing. All of them are possible, but some are more stabilized than others. Oh, okay, yes.
So if that hydrogen was substituted for something that had occupied p orbitals, there would be no stabilizing bond?
Right, so this is only stabilizing the carbocation. And carbocations are high energy inherently, and they will find ways to either be satisfied through having electrons come from another source to them or through structural rearrangement. But carbocations are they're inherently unhappy versions of a compound. So this is able to happen because there happens to be this vacancy because we don't have enough electrons. But the second you have the iodine or halogen come in, it's going to put the electrons there, and then you're not going to have hyperconjugation because there's no place for it to go. Well, no, you will, the way you have it here. Because you can still have alignment of bonding and antibonding orbitals in terms of their conformers, whether it being eclipsed or staggered, with the staggered being more stable. It just won't be due to having a vacant p orbital with a charge. Same general effect of through space distribution of electrons, but for different rationales. Go in different places, yeah.
So the carbon with the positive charge on it, it will never have hyperconjugation with one of those hydrogens that's bonded to it?
You mean like this hydrogen?
Yes.
No, because this only has an s orbital. And its electrons are fully committed to this sp2s sigma bond already.
So more has to do with the sp3.
Right. Exactly. That's why a tertiary is more stabilized than a primary because the hydrogen bonds can't hyperconjugate.
Okay.
The bonds to the hydrogens, since hydrogen bonds are something else entirely. Good question. All right. Okay. So it's interesting because I like explanatory power and rationalizing rules. It's really common when people are doing OChem for the person to just say, this is Markovnikov's rule, and the substituent always goes to the place that has the most carbons bound to it. And then they leave it at that. But everyone's like, oh, okay. Why? I'm like, don't worry your pretty little heads about why. This isn't just chemistry. So even though it's a little bit deeper down the rabbit hole than a lot of folks go, I think it's nice to have actual explanatory power, and you can kind of see the same effect pop up over and over and over again that way. So let's talk about the state, the structure of transition states, and some of the theory about how we predict what a transition state looks like and why it might form more rapidly. So if we are looking at a reaction coordinate diagram, and we're looking at this being reaction progress, and this is increasing energy. If you think about a reaction progressing from one side to the other, it doesn't make rapid, spectacular changes. As it progresses, bonds are being stretched, bonds are being compressed, a stretched bond eventually breaks, the compressed bond potentially forms a new bond. So as you move this direction, you're getting, this is a terrible analogy. It's like a transformer. It has to like actually go from one form to another one, except unless it's one of the new Transformer movies, and then it's just a bunch of like magical garble that happens that violates all of the rules of conservation of mass in the universe. But not that I'm bitter about the new Transformers movies ruining my childhood memory of something that was great. That, the Hulk, Ninja Turtles, they ruin everything. Star Wars,
Keep going.
oh my goodness. So if we have 2 points on the curve here, the structure at this point, when it's in this state, is going to be very different than the structure over here, especially since we've gone through this high energy transition state in between. But if we have a point here and a point here, structurally, the two structures that are responsible for this energy level are going to be very similar. So the closer you are together on a reaction coordinate diagram, the closer the structures are going to be to one another, which is what rationalizes them being so close to each other. Because it is just a linear path of a reaction taking place. So because of this, if we have an exergonic reaction versus an endergonic reaction. Let's see here. If we look at the distance of the reaction progressing coordinate, and we go from the reactant to the transition state, we've only traveled this far in terms of the path of the reaction. We go from transition state to product in the endergonic reaction. We're about that far. But if we're looking in terms of the whole distance from this transition state to the product is greater, and to reactant is greater. So what this means is, in an exergonic reaction, the structure of the transition state is more closely going to resemble the reactant than the product. And for an endergonic reaction, the structure of the transition state is going to more closely resemble the product than the reactant. So we can get some insight into what the structure of the transition state likely is based on the structure of either the reactant or product, depending on whether or not it's exergonic or endergonic. So the formation of a carbocation is endergonic, which makes sense because we're going from here to here. It requires energy to do it because we're going to a higher energy state for this transition. So in this case, the transition state is going to more closely resemble the product. Now, when you read that the first time, you probably thought, well, that doesn't make sense because I thought that we were ending up in a more stable place. But it's easy to forget for reference. At the reaction as a whole is product, transition state, high energy transition state, high energy intermediate, secondary transition state, product. So what we're looking at is that slice forming the product, which is your carbocation. So the transition state to the carbocation is going to more closely resemble the carbocation, which means it's likely going to have partial positive charge before it has full positive charge. And that charge is going to be located near the carbon, which is more substituted. Yeah.
Why would you not draw the red arrow on the exergonic one from the T?
Arbitrarily. I'm just trying to give visual distances for people who are sitting a little further away, so you can see that the transition is closer to this side than this side, and the transition is closer to this side than that side.
Oh, it's all about like that.
Yeah, because this entire coordinate is reaction progress.
Oh, okay. I see.
Yes.
If you have two points on that curve that are directly across from each other,
Mhm.
from sides of the curve, are they getting a similar structure? Or because
No.
okay, even though they're like the exact energy. level,
So if we had
they're
a
overlapping.
place here and a place here, they're actually quite distant from each other. They're the same energy, but they're distant in terms of reaction progress. So the rationale is that they're very close to each other on the reaction progress coordinate, not necessarily the energy level. Because there's lots of compounds that have the same basic energy level that are unrelated. Good question.
I'm just clarifying.
Yeah.
So it's by x coordinate distance, not y coordinate distance. I got lost as soon.
Reaction progress is this one, and
Yep.
this is just energy.
Yes.
So, yeah, x coordinate distance. So, to clarify, because of this rationale, we can assume that the transition state of forming a carbocation is also going to have positive charge or strong partial positive charge, and that partial positive charge is going to be located more closely to the more substituted carbon. And this is going to cause it to form more quickly, which is why it will get attacked more frequently, which is why we end up with the more substituted carbon getting the secondary attack as well. Okay, we got 15 minutes. Any other questions before I erase it forever? Okay. What am I doing? What's next? Okay, so because of carbocation not having equal chance necessarily of going to either side of the double bond, that means that the second nucleophilic attack is not going to necessarily go proportionally to either side of a double bond. And this gives us to a new term that this chemistry has Regio Selectivity. So, in the case of this compound, if we put it in the presence of hydrochloric acid, get our first attack, kick off the chloride. We have two options.
Is that free electrons there?
No,
I think or is that just remnant from?
I think it's just
Erasing.
yeah. There was no flipping.
No, it was remarkably like a ghost pair of electrons. We can either go with putting the positive charge here and the first proton over here, or we can put
I think you dropped an H on second. That one there.
there we go. So which one is more stable as a carbocation?
Tertiary.
The first one, because it is primary, secondary, or tertiary? Secondary, because this carbon, which is the carbocation, has 2 carbons bound to it and 1 hydrogen, so it's secondary. And this one is primary, so secondary is preferred over primary. So although we'll do both attacks, just in this particular case, this is the compound that is highly preferred. I'm going to say highly preferred because we'll probably get a little bit of this forming as a minor product. So we can call this a major product. This one our minor product. In this case, because it's primary, it's going to be a very minor product. If this was a tertiary and this was a secondary, it would be nearly 100%. This with almost no measurable synthesis of that. Let's do another one. Aha. At this point, everyone's probably getting the hang of doing this, and you want to be able to push the electrons, but you also want to be able to skip some of the electron pushing and just predict what product will form. So from here, what is more likely without pushing electrons? This or
First one.
votes for first one?
It's tertiary.
Yes, because the bromine is going to do this attack where the carbocation is most stabilized, which is on the more substituted carbon. In this case, tertiary one. And this is a secondary. So tertiary versus secondary, tertiary wins. This will be our major product. This will be our minor product. And this is called Markovnikov's rule. And I mispronounced it for a majority of my first decade of chemistry because when I took it, a person who I learned it from called it Markovnikov's rule. And I didn't realize until I'd lectured in OChem for like 3 semesters, somebody's like, why do you call it Markovnikov? It's spelled Markovnikov. Really? Oh, it is. So it's I'm retraining. So if I start to mispronounce it or change midstream because I'm trying to pronounce it correctly, that's what's going on. Let's see here. So Markovnikov's rule is that electrophiles add to the sp2 carbon bonded to the most hydrogens.
Can you say that again?
I'm going to write it down.
Okay.
Well, I'm just literally copied this from the book. I think I did, anyway. So, the electrophile in this case is what? That's our electrophile. So the electrophile is going to go to the carbon on the sp2 carbon. So this is an sp2, this is sp2, which is why we can have a single pi bond, and it's planar. and it's going to add to the carbon which has the most hydrogen. In this case, this carbon has 1 hydrogen, this carbon has no hydrogens. So it's going to go there. Because the carbocation, I mean, it's all rationalized by where the carbocation goes. It's funny, though, because when I learned this, shows you how much I was reading the book the first time I took OChem. It was explained to me that Markovnikov's rule was that the second nucleophilic attack was on the more substituted carbon, which is where I always go. And you get to the same place at the end, but this is actually what the rule is, not some restated version of the rule. So, but if you go with where the carbocation is stable, it's harder to go wrong. I was going to say you can't go wrong, but that sounds like a challenge. So let's do some different, not hydrogen halide substitutions. Let's add water across a double bond. So typically, if you put an alkene in water, you're not going to just get spontaneous reaction because water is not a very good acid, and this is an acid catalyzed reaction. So because it's such a poor acid, it's stable. That and most alkenes are going to not mix well. You have to spend a little bit of energy to get them into water to do this reaction. But if we add a strong acid catalyst, that changes it. So in this particular case, let's say we have some general terminal alkene, and we've got water, and this is going to be a reversible reaction because all the steps are reversible, and we put in a little bit of sulfuric acid. What we should get is I could just call that a CH3, but I want to show that we have a hydrogen substituting an alcohol. So we start with an alkene, and we're ending with an alcohol as a product by adding water across the double bond. So what does this look like mechanistically? I'm going to show what the book shows, and then I'm going to do a little twist on it because I think it's a more realistic version of the same mechanism. So mechanistically, if we have throw this up here, so sulfuric acid, where's my H? H2SO4. What's our nucleophile? Where's our electrophile? Right, we've got our first proton, which is a strong acid. So we can take these electrons from the double bond, do our first attack on this proton. This proton's very good at dissociating because it's a strong acid. So there'll be no issue at all at taking these electrons and putting them over here because it likes to do that spontaneously in water. But, let's see here, this is a slow step. So I'm going to draw with a larger one-sided arrow in the direction towards the reactant and a shorter arrow towards the product. It's kind of a good shorthand for saying something slow versus fast, or you can explicitly write it as slow. And once we've got this, where's the carbocation prefer to go? The secondary carbon. So what happens then, according to this mechanism, is water can now come in. The lone pair on the water can do an attack on the carbocation. This is a fast reaction because carbocations are not stable, and this wants to happen. But when this happens, we haven't brought any new electrons to the party. And this is not charged. This is neutral, and this is positively charged. So the net for the system is got a +1 charge. We can't lose that charge. This lost an electron to share it with this carbon. So now this oxygen is positively charged. And as everyone knows right now, in your gut, you're thinking, oh goodness, that is not a happy oxygen. And you're right. But luckily for you, because this is acid catalyzed, we can come in with another equivalent of water, because water is abundant in this reaction because we're combining it with water. And take one of these protons, break this bond, push those electrons to the oxygen. Oh, wait, I didn't draw the rest of this. And we're going to form the alcohol. And have hydronium as a product. And that hydronium as a product works mechanistically because we're in an acidic solution, so it's favorable to form the acid as a product. So we're not actually consuming the proton, we're just utilizing it catalytically. Now here's the part of this mechanism that I don't like. They're setting you up to do the same mechanism with an alcohol next instead of water. So they're showing catalytic use of sulfuric acid as the first step. However, mechanistically, you're probably going to have more water in this reaction than you do alkene, right? To help drive things towards product. What does sulfuric acid do in water? It fully dissociates. And by fully dissociates, that means it makes a whole bunch of H+, which is in water hydronium. So we could also do this exact same reaction by saying sulfuric acid plus water produces hydronium plus HSO4 minus, and we could have hydronium be our first attack, which is the way I see this done more commonly in water, and I think it's a more realistic representation of what's happening. So this can attack the acidic proton, which is exactly the same as attacking the acidic proton on the catalytic quantity of sulfuric acid, but now we produce water. Water comes in with a rapid second attack, and then a second thing of water deprotonates the charged system, giving us the alcohol. And it also is neat because we start with hydronium as a catalyst and we end with hydronium as a catalyst, which I think is a little tidier also. Both are valid, and you'll see how the other one is potentially more valid when we do the next mechanism next class. Yeah?
Why do we need the sulfuric acid at all if water dissociates on its own?
Because it's a really terrible acid. It'll associate so minimally that it's not going to actually drive the reaction at all.
Or just slowly?
Inconsequentially. Yeah. Yeah. This is acid catalyzed. Yes, because we're not consuming the acid. We initiate it with the acid and then we reproduce the same amount. So this is acid catalyzed. Yes.
So is the reason why HSO4 minus doesn't take the hydrogen off the protonated alcohol? Is it because there's a lot less of it?
It's because the stronger the acid, the weaker the base. And because it's a strong acid, it's a very, very weak base. So it's not really looking to get that proton back. I'll see everybody Monday.